We started our study of StatMech by thinking about an isolated system. An isolated system being one which conserves the total number, volume, and energy. And we sort of postulated a couple of things for that ensemble, right? The NVE ensemble. We said all states are equally probable. Uh, you are Julio, look up midterm and things on the website, okay, or ask your friends.
Okay.
And so we studied NVE ensemble, which is isolated ensemble. Then we went to a canonical ensemble, where the system can exchange energy with the bath, with the environment. Total, we said system plus bath is an isolated system. So this is also known as the NVT ensemble. For NVT ensemble, we said probability of finding the system in a certain microstate nu is proportional to the energy of that microstate, which is not the same as probability of finding the system with a certain energy. Okay, this subtle point I want to drive home again. P of E is not equal to e to the power minus beta E. P of E is equal to omega of E multiplied by e to the power minus beta omega E. Okay, P of E is proportional to omega of E to the power minus beta E. And to be more precise, P nu is equal to 1 over Q e to the power minus beta E nu, where Q is the canonical partition function, which depends on NVT, because these are our control variables here. And this is going to every microstate and summing e to the power minus beta E nu for that microstate. And we then showed what is the connection of thermodynamics with this Q, because Q is just some abstract number we calculated for this setup, right? We don't know how it connects to something we can measure in the lab. You cannot just go and measure Q in the lab. Now you might say, if I have solved a problem in quantum mechanics, I know my energy states, right? I know the ground state. If I know the energy of the ground state, if I know the energy of the first excited state, then you could calculate this thing explicitly, right? Does everyone agree with that? If you have solved a hydrogen atom, for example, you know the energy of the ground state, the energy of the first excited state, right? So you could go and plug those values over here. But the first problem is you have to go to all excited states. You cannot just stop at the first excited state and be done. They will contribute exponentially smaller amounts, but they will keep contributing, right? So you have to do the summation, and you don't know what's going to happen. So we connected this to thermodynamics, and if you remember anything from 684, the state function that depends on NVT in thermodynamics is the Helmholtz free energy A. So no surprise, here also the connection comes through A, and A is equal to minus kBT ln log of Q NVT. And we then looked, since energy changes in this ensemble, we looked at the average value of the energy. Average value of the energy was something like minus partial ln Q by partial beta at constant NNV, right? We got something like that. We also derived the fluctuation in energy, and we showed that the fluctuation relative to the mean goes to 0 as n tends to infinity, right? So it becomes the same as the microcanonical ensemble as you approach thermodynamic limit. Today, what we are going to start is the grand canonical ensemble. Here, the system does not exchange only energy. It also exchanges particles. So it's this thing, right? The molecules, water molecules are escaping as steam or vapor into the atmosphere, right? The canonical ensemble was, when this was closed, it's not insulated, so it exchanges energy until it comes to the same temperature as the room. Now, if I open this, it can also exchange molecules, right? So, and the same idea we will follow as we did earlier. In order to derive things for this, we will again embed it in a bigger bath. And we will say system plus bath is fully insulated. What we are going to show today is the probability of a microstate in such an ensemble comes out to be proportional to e to the power minus beta e nu. That term shows up again. But now we have a second term, which is plus beta mu n nu. Beta is the inverse temperature. Mu is the chemical potential of the system, of the particle in the system, right? So when you allow energy to exchange, energy exchanges until temperature becomes the same. When you allow particles to exchange, they exchange until the chemical potential becomes the same, right? That is the sign of thermodynamic equilibrium. When you allow volume to exchange, it changes until pressure becomes the same, right? So that's why we have three things always. So this ensemble is also known as the mu Vt ensemble. The control variables here are mu, V, and T. So P nu is proportional to these two things. And more precisely, P nu, if you want to get rid of the proportionality constant, you introduce a variable z, and then you have e to the power minus beta e nu minus mu and nu. And z is again the partition function. In this case, it is the grand canonical partition function. We will work through it. Z depends on mu Vt, and it is given going to every microstate. And now you sum up not just E nu, you sum up beta E nu minus mu and nu, something like this. And we will show that just like we did Helmholtz free energy connected to the canonical partition function, we will show that there is something that is connected to the log of grand canonical partition function. From thermodynamics, you expect it to be the state function whose natural variables were mu Vt. Does anyone remember what is the state function whose natural variables are mu Vt? Huh? Close. Good guess. It's NPT. Gibbs free energy is NPT. It's a very strange function that we rarely use. It's called the grand potential, and it's denoted omega g. Grand potential is minus kBT ln z, and what is this grand potential? It more precisely, it is defined as A minus mu n. It is Helmholtz free energy minus mu n. Okay, this is something we don't study in physical chemistry undergrad level. We definitely don't study grand potential. In 684, you kind of hear about it, but then you forget. It shows up in statistical mechanics. So it's A minus mu n. And like I said in the beginning of the class, I'm going to give you some practice problems today, which will brush up your thermo and will also allow you to work through StatMech, okay? So this is practice problem 1. Go home and show, not go home right now, we'll go home later, and show that this is the same as minus PV. This A minus mu n is nothing but pressure multiplied by volume with a minus sign. Okay? So try that, work through that algebra. The thermodynamics of that should be clear. If not, you have some work left in revising your 684. Okay, so this is what we are going to show today, and you should do A minus mu n is equal to minus PV at home. So let's get started. We will follow the same approach as we did for the canonical ensemble. We will consider a system. Let's make a perforated boundary which can exchange number and energy, particles and energy with the environment, right? This is my system, but I can't do anything. So what I'm going to do now is to embed it in a much, much, much bigger system, which I call the path, right? That's how I did the canonical. So I draw a much bigger system around this, which I call the bath, okay? And then I say that system plus bath together is fully insulated. Furthermore, I assume that system is much smaller than bath, okay? So the total number of particles in system plus bath will be n bath plus n nu. At any given microstate, the system has n nu, and now we are talking about n nu, not just n, right? Because we are allowing n to change. And if n nu goes up, nb will go down. If n nu goes down, nb will go up, right? So that the total sum of both is constant. Same thing for energy. E is equal to EB plus E nu. If E nu goes down, EB will go up, and vice versa. And since system is much smaller than bath, we are assuming E nu is much smaller than EB. We are assuming N nu is much smaller than NB, right? So, for example, number of coffee molecules or water molecules I have in this cup is really very small compared to the amount of water which in this room currently, right? It's much smaller than this room is much bigger than this cup. That's the idea over here. So if you recall the proof that we did for canonical ensemble, we are going to follow exactly the same proof. We are again going to use Taylor series. Now we will have Taylor series in two variables, right? Because we are changing two things. There are two things that are kept small. So what did we do last time? We looked at number of ways the bath can exist, given that its energy is EB and its number of particles is NB. So that will be omega B, the macrocanonical partition function of the bath, as a function of E minus E nu and as a function of N minus N nu. Okay? When we did the canonical, we wrote omega B of E minus E nu. And we are assuming that omega B, the number of ways the bath can be arranged, is much more than omega system, the number of ways the system can be arranged. So, and I'm going slightly faster than the proof that I did last time for canonical. Last time I made tables and really counted ways. I'm just running through that argument. So the probability of finding, this is still Chandler chapter 3. He doesn't even go through this proof. He just gives you the result. He says, do it yourself. He was very lazy. Probability of finding the system in a state nu will be, this is P nu, and that will be proportional to omega bath E minus E nu N minus N nu. Okay? In reality, it will be proportional to omega bath E minus E nu multiplied by omega system E nu N nu, right? In reality, the probability of finding the system in a certain state will be the product of these two things. It will be proportional to the product of these two things. We are going to ignore this one. Why can we ignore this one? Because later we are going to work with log, right? When you take the log of this thing, log of omega bath will be much bigger than log of omega system. So we are just going to ignore our omega system and not write that much algebra. But in reality, omega system is much smaller than omega bath. Therefore, log omega system is much smaller than log omega bath. Okay? That's what I scribbled over there. So that's why we ignore this thing. So the probability of finding a microstate, the system in a microstate nu is proportional to omega bath E minus E nu and minus N nu. So let's continue from here. So if P nu is proportional to omega B, E minus E nu, N minus N nu, then log of P nu is proportional to log of omega B, E minus E nu, N minus N nu, right? So this is where you would have had plus log of omega cis, E nu, N nu, right? But we ignore this part because it's a much smaller number than log of omega B. So now remember that E nu is much smaller than E and N nu is much smaller than N. So we are going to do once again our Taylor expansion of omega B. Now it will be Taylor expansion in two variables. We will do Taylor expansion around E and N. So let's call this equation number 1. Equation 1 gives ln P nu is approximately ln omega B at E and N. Notice this does not depend on nu. This is a constant. This is E is the total energy of system plus path. N is the total number of particles in system plus that. What should be my next term when I do Taylor series? Gradient of what? Of the whole. Log of omega b with respect to energy at constant n volume multiplied by dE. What is dE in this case? It's E nu. That's the small difference we are thinking about, right? So dE, normally when we do Taylor series, we have derivative multiplied by differential of the thing, right? In this case, dE is the same as E nu. So what we have, and the third term will be minus partial ln omega b by partial n at constant E comma v multiplied by dn. And again, dn is the same as n nu. Okay. So what do we get? We get ln p nu is proportional to some constant c naught. Okay. This does not depend on nu. So let's just call it c naught, some constant c naught minus partial ln omega b by partial E at constant nv multiplied by E nu minus partial ln omega b by partial n at constant EV multiplied by n nu. Now comes the moment of truth for you all as to how much you are actually keeping up with me. Two moments of truth, one easy, one harder. Have you seen this before? Vivian, what do you think? What is log of microcanonical partition function? Hint, most famous formula. Entropy, correct? So we have partial entropy with partial energy. Does that have a thermodynamic name? Temperature, absolutely correct. So we have to be a bit careful. It is 1 over temperature, right? So Vivian passed the moment of truth. So this becomes ln p nu proportional to C naught minus beta E nu. Second one is harder. This is easier to forget. Once again, she already helped you. Ln omega is S, right? So this is partial S with partial N. Does that have a name?
Minus mu over T.
Yeah, but you're on Zoom. Are you looking up the internet? I don't believe
No.
You get negative price.
I knew it.
Fine. This is plus beta mu multiplied by n nu. And this is your practice problem number 2. Since not all of you jumped on me with saying, oh, that is plus beta mu, you have work to do. How would I derive this? I forget this one. The first one, the minus beta one, is easy to remember. Derivative of entropy with respect to energy is temperature. This one is harder. In thermo, when you're stuck with anything, which equation do you start with in thermostatic? Integrated first law. You get price. I don't know what the price is. So tell me, what's the integrated first law? dE is equal to TdS minus PdV plus PdN. So what I will do here is to bring TdS to the left side. TdS becomes dE plus PdV minus mu dN, and immediately you can see that minus mu over T is equal to partial S by partial N at constant E and V. Okay, so this was practice problem 2, but go again home and do it. I'm going to erase this deliberately, so you go and do it yourself. Okay. Okay, you'll remember maybe. So, and then on the same note, try to see if you can derive pressure from microcanonical partition function. Okay, the problems that you solve in StatMech, all you do is to calculate the partition function and derive thermodynamics out of it. That's the whole idea, right? So these type of relations are very important to make your calculation useful. So now we have, let's call it equation 3. ln p nu is proportional to C naught minus beta E nu plus beta mu N nu. Okay, so we can take exponential of both sides. If we take exponential of left side, e to the power ln p nu is going to be p nu, right? E to the power ln p nu is p nu proportional to e to the power constant. That is a constant. Why worry about it? It's just a proportionality constant. E to the power minus beta E nu, e to the power plus beta mu N nu. Or p nu is proportional to e to the power minus beta E nu minus mu N nu. And that's the probability of microstate in a grand canonical partition function. Chandler generalizes this. Chandler talks about generalized forces and say instead of mu and n, if you had something else, then you could write down a relation for that also, and you can think about that, right? Mu and n are conjugate variables, just like beta and energy are conjugate variables, and you can do things like that. Any questions about this? Yeah.
So why, this is kind of just like curiosity, but why is it standard to have like minus beta rather than just beta and distribute the minus out? Like I always see it written like this. Is positive E mu like minus like mu in, like, is that like a quantity that's going to return later? I always
It did not return later. This is how it showed up, right? Here you had plus beta mu and mu.
Yeah, but we factored out a minus beta. Is there a reason we don't factor in that minus and then say it's like mu in minus?
No, you could.
Because,
Are you saying that you want to write it as e to the power beta mu
Yeah.
n nu minus e nu?
Yeah, I just always see it written the way you wrote it. I don't know if there's like a reason.
Because we start with canonical ensemble, right?
Okay.
So we think about e to the power minus beta e nu. It looks like the Boltzmann factor. So just to stay similar to the Boltzmann factor, you can always write it that way also. Nothing stops you. It's just notation. Okay, good. So what do we have? We have p nu proportional to e to the power minus beta E nu minus mu and nu. And again, you could have written it out as e to the power plus beta mu and nu minus e nu. It's the same thing. So what is the proportionality constant? We give the proportionality constant a name. We call it Z. Some books use different symbol. What really matters is what does Z depend on? In this case, Z depends on chemical potential, volume, and temperature, multiplied by e to the power minus beta E nu minus mu and nu. This is the grand canonical partition function and its probability of microstate. So we call this equation number 5. And Z mu Vt is summation over all microstates of e to the power minus beta E nu minus mu and nu. This is grand canonical partition function, equation number 6. Yeah.
So the C term, that just comes from the CO?
It includes CO also. It is coming from CO, but we don't care, right? It came from e to the power beta CO and things like that. So you could go back and write down CO explicitly in terms of it, but CO was something we just put in for laziness, right? So you don't need to remember that. What you do need to remember is that probability is proportional to this thing, and Z is the proportionality constant. That's the grand canonical partition function. Thanks. So, and again, I will write down because it's so important that for microcanonical, which is NVE, that's the first one we did. Then we did canonical, which is NVT. And now we just did grand canonical, which is mu VT. For all of them, we can write down the partition function. In this case, the partition function was omega NVE. In this case, we wrote down the partition function as Q NVT. In this case, we wrote down the partition function as Z of mu VT. For omega, we know the relation. Connection to thermo is S is equal to KB ln omega NVE. For Q, the relation is A is equal to minus KBT ln Q of NVT. For this one, now we are going to show the relation is Grant potential omega g, which is the same as minus PB is equal to minus KBT ln Z of mu Vt. So if you are working with an ideal gas, you can already see something interesting that should be happening. For an ideal gas, PV is equal to nRT, right? So for an ideal gas, Z, ln of Z would be constant, independent of temperature, which is kind of interesting, right? Remember, PV is equal to nRT for an ideal gas. So if you put in PV is equal to nRT in this omega G equation, then T cancel out, and you are left with ln Z is equal to constant, or Z does not depend on temperature, which is kind of interesting result for only for ideal gas. So, but we need to show right now that omega G is equal to this minus PV. The proof will be similar to what we did for Helmholtz free energy for canonical partition function. How did we do Helmholtz free energy for canonical partition function? First, we worked through the fluctuations. Remember, we calculated the average energy. Then we calculated the fluctuation in energy. And we showed that the fluctuation in energy goes to 0 relative to the mean as you go to the thermodynamic limit. So recall, for canonical ensemble, we showed that fluctuation in energy by mean of energy goes to 0 as n tends to infinity. Remember, we had that relation. How did we do this? That had us derive the very interesting relation that variance in energy is proportional to the heat capacity. Right? That's the idea we used. And since heat capacity is extensive, variance in energy is extensive. Therefore, standard deviation in energy is intensive. So for grand canonical, we can show a similar thing. Similarly, we will show that for grand canonical ensemble, once again, fluctuation in energy by mean in energy goes to 0 as n tends to infinity. And not just that, there is one more thing fluctuating here, which is the number of particles in this system, right? We will show that the fluctuation n by the mean n also goes to 0 as n tends to infinity. Once more, we are going to show that the grand canonical ensemble also becomes the same as the microcanonical ensemble as you approach the thermodynamic limit, right? So the grand canonical ensemble will have an E bar, and we are saying that for all practical purposes, E approaches E bar, and N approaches N bar in thermodynamic limit. So I'm going to show this in a bit. Before I show that, I want to work through the proof that omega G is minus KBT ln Z. Okay, I'm going to use this, and then later I will come back and prove this. Okay. So using this, I want to prove that omega G, which is defined as A minus mu n, which you will show at home is the same as minus PB, is equal to minus KBT ln Z of mu Vt. Okay. So the proof will follow what we did for canonical ensemble. We are going to assume thermodynamic limit. We assume, because all of this is only for very, very large n, right? So we are working with thermodynamic limit. We assume thermodynamic limit. And now we know, or we will prove in a minute, that in this case, n tends to n bar and E tends to E bar for grand canonical ensemble. So remember, when we proved this thing for canonical, we switched to using relations for the microcanonical ensemble. That is the whole thing we are going to do here also. So once again, we will use the entropy formula for microcanonical, which is plus KB ln omega. And instead of NVE, now we will write down N bar. Volume is constant, volume is not fluctuating, and E bar. And now we can use the formula for probability in a microcanonical ensemble. Probability in a microcanonical ensemble is 1 over omega, right? All states are equally likely. So this will be minus KB ln probability of E bar V N bar, right? Using microcanonical formula. And the reason why this proof is so interesting is because one time we use microcanonical once it suits us, and when it suits us, we use the formula for that ensemble. So now we need a formula for P of E bar V N bar, which is something we just derived in equation number 4, that P nu is proportional to e to the power minus beta E nu minus mu N nu, right? Let's call this, yeah, equation 5 is what we need now, that probability of the microstate is given by this thing. So use, this is equation 7. So use equation 5 in 7. What does that give us? Let me write it down on the next page. So we had equation 7 was S is equal to minus KB ln P of E bar comma N bar. And I'm ignoring volume because it is constant, just being lazy. And we know that this thing is e to the power minus beta E minus mu N, right? So we are going to use that relation. So S is equal to minus KB ln e to the power minus beta E bar minus mu N bar divided by Z, right? So now we can, and this is really, we are talking about S bar. We are talking about the average value of the entropy in the thermodynamic limit, right? So in all of what I am writing, it should not be S, it should really be S bar, because it's coming from, I hope you can still see my screen, Noah.
Yeah, I can.
Okay, good. So S bar is equal to minus KB ln of this thing. Ln of e to the power minus beta is what? That is just minus beta, right? So this becomes minus KB minus ln Z minus beta E bar minus mu N bar. Okay. So S bar is equal to plus KB ln Z minus plus KB. Let's go slowly. Plus this minus and minus becomes plus KB 1 over KBT E bar minus mu N bar. Okay, KB cancels, wonderful. What are we left with? We are left with S bar is equal to plus KB ln Z plus E bar by T minus mu N bar by T, or minus KBT ln Z, I multiplied both sides with temperature, is equal to E bar minus TS bar minus mu N bar. Does E minus TS have a name? What do you think, Julia? A. Helmholtz. It's 26 letters, huh? U is what we use for E, so it's not going to be that. So this is A, the Helmholtz free energy, A bar minus mu N bar. And that is what we defined as our grand potential, right? Omega g is equal to mu ns n bar. So we have just shown that omega g, which is the same as minus PV, is equal to minus KBT ln z. So my biggest concern with all of you, each and every one of you, in doing well in this course is rustiness with thermal. Okay, and this is not a judgment on anyone. This is how it happens. You forget, especially if you have not taken 684 or PChem was a while ago, or if you have a license plate that says honk if you pass PChem. I have seen one. Then you're going to be in trouble. You will be able to solve things and you won't be able to get to the final part, because almost half the problems or more than half the problems will have you calculating something and doing something with it, right? Which is like calculate thermal expansion coefficient, calculate heat capacity, draw a plot of this, draw a plot of that, blah, blah, blah. All of that would involve knowing the right state functions that connect with that ensemble and knowing the right relations to manipulate that state function, okay? So this is why the homework has a lot of problems. So you keep working through it. So we have just shown that omega g is equal to this thing. Any questions about this? And again, practice what I preach. Anytime you write things like this, you should always write the variables it depends on. Otherwise, there is recipe for disaster. Z depends on mu Vt. If you study Macquarie's book, it does not call it Z. Some book will call this as Q. Does not matter, okay? What matters is what variables does it depend on. There's a lot of algebra, I know. But it's not very complicated algebra, but too much algebra for chemistry, perhaps. Depends on what you like. So, we just take another, let's go up by 20,000 feet and look at the general framework of what we have been doing so far. For all three ensembles, we calculated or we wrote down something about the partition function, right? For microcanonical, it was omega. For canonical, it was Q. For grand canonical, it was Z. Some name, does not matter, right? Partition function on its own was not, it's kind of meh. You don't do much with it, right? It exists, it's fine. The first thing that is useful is the log of the partition function, right? That is Boltzmann's formula for entropy. That log of omega gives you entropy, correct? Entropy is a state function. Yes or no? Yes, I hope everyone agrees. Similarly, for Helmholtz, for canonical partition function, we saw that log of Q gave us Helmholtz free energy, another state function, right? For grand canonical partition function, we saw log of Z gave us omega G. Is omega G a state function or not? Disha, what do you think? Good answer. Why? And what does it depend on? More specifically, it's okay, very good answer. Omega G does depend on mu Vt, but if I think about this equation, it depends on pressure and volume also, right? And pressure or volume are state functions. That's how you define the state. So omega G is also a state function. So a general trend is emerging that log of partition function gives us a state function, right? For all of them. That's the first way in which partition function becomes useful. You take its log and it gives you a state function. But that's not the only thing. For canonical partition function, we showed that, where did it go? E bar is equal to partial derivative of log of partition function with respect to something else, right? So partial derivative of log of partition function with respect to something which is intensive or extensive, doesn't matter, it can change, gives us average of a state function. So notice the difference between 1 and 2. 1 gave us S, 2 is giving us E bar, right? E bar is different from S. In the thermodynamic limit, average of a state function and a state function is the same thing. But in non-thermodynamic limit, these two things different when not in TD limit. Okay. And just an example of this example, E bar is equal to minus partial ln Q by partial beta at constant n and V. Why am I writing this down? Number one, because I think it's cool. Number two, anytime a problem asks you to calculate the average of something, your brain should go, aha, this means I have to take the log of partition function and differentiate it. Why is this useful? If your partition function has a bunch of constants, you can be like, I'm not going to care about that. This will be like the C naught from earlier. If you were dealing with number one, if you were dealing with the actual state function itself, you cannot get rid of the constants, right? That C naught would matter because it would be log of C naught plus this other thing. But if you know that you're going to differentiate it once, why do you care? You just ignore it, right? So you develop such intuition. That's the second level of hierarchy. This is like the movie Inception. Okay, now we go one level deeper. Second derivative of the log of partition function with respect to, again, something intensive or extensive. This corresponds to fluctuations of some state function. We saw this for the heat capacity. Remember, we deal with double derivative of log of Q with respect to something, and that's how we count the fluctuations in energy. When we derived all the business for fluctuation in energy, we had to differentiate it twice. So remember this general framework. It will be useful as you go further in this course, but also in your future life. If you keep doing science, which I hope you do. The current environment is not making people excited about doing science. There's no doubt about it. And and these type of relations apply to all of equilibrium StatMech. We have seen 3 partition functions. And if you really want to practice and get ready for exam, just work through it. Just especially these days, since you have Bing and ChatGPT to help you, just go wild, like calculate the partition function for a canonical ensemble. Think about some variable, go differentiate it, work through the math, just go for it and see what you get. And then cross-check and see whether it makes sense or not. And this way you can really, especially if you go to the second derivatives, you will get some interesting relations and have a lot of fun. Okay. So what I need to do, any questions about this? Okay, Disha is saying no question. Everything is clear to her. If there are any doubts, ask Disha. So what we want to do next, just like we showed E bar in canonical ensemble. And again, I have written down this formula many, many times today, so you should remember, okay, it's important. Minus partial ln Q by partial beta. Also, it's totally possible that even though I wrote down so many times, each and every one of them is wrong. I might have forgotten it, but you get the gist of it, right? So go and check, don't take my word. For canonical ensemble, now we will show similar relations for grand canonical ensemble. The first one will be n bar. N bar is going to be 1 over beta partial ln z by partial mu at constant volume and beta. What else fluctuates in a grand canonical ensemble? Number fluctuates. What is the other thing that is fluctuating? Is the temperature fluctuating? No, we have put it to be constant, right? We are calling it a mu VT ensemble. So the temperature shows thermodynamic equilibrium. So what is fluctuating then? Energy. So we need to write down something about the average value of the energy. That we will show, or rather you will show, comes out to be minus partial ln z by partial beta at constant mu and v. So this expression looks just like the one we had for canonical, but it's not quite true because we also have a plus mu n bar term that shows up over here. And the third thing you can show is the pressure. You can also calculate the pressure, and the pressure turns out to be plus 1 over beta partial ln z by partial volume at constant mu and beta. Okay. And I'm going to show the first one. These two are practice problem 3 for you. Work through them on your own. Don't try to open up notes. Just follow what I'm doing for n bar and see how far you can get if you can derive the whole thing. If you can, then you are in good shape. Okay. And you might need to, if in doubt, invoke Tucker telling you just use the integrated first and second law, right? If in doubt in all of this course, just start with first and second law. The pathway will be complicated. It might take up your whole exam time, but you are guaranteed to get there, okay? So it's spontaneous that you will get there. Kinetically, we don't know how much time it will take. You will get there in the age of the universe if you start with the integrated first and second law. And after spring break, there will be homework number 3. Some of these practice problems I will put again on the homework number 3. You know, just you have done it. Just it's a lot of practice, right? It's practice, practice, practice. You can ask Julia. She plays piano, right? So you probably have played the same piece maybe hundreds of times, right? That's what it is, right? So you need to practice these things again and again and again until it becomes really second nature. So we are going to show this one today, and then we will stop. It won't take a lot of time. N bar is equal to this thing. So to prove this, what should we do? How should we start even? What is physically going on here? The system has one macroscopic state, right? That mu is constant, volume is constant, temperature is constant. And the number of particles in every microstate change, they fluctuate. So how do we calculate n bar? How should we proceed? What should I write down? How should I even start? Any ideas?
So times of mu times the probability of getting that number of particles in each micro.
Correct. I want to make sure Atli is on the same page as me. Atli, do you agree with what he said? You don't agree fully. Why not? So this is what I want you to agree with, or tell me if you don't agree with. So I go to every microstate. Then I look at the number of particles in that microstate. This is not sufficient, right? Because this is not accounting for the fact that every microstate has a different probability. What is that probability? P nu. Okay. Do you agree now, Atli? Good. Do we know the expression for P nu? Which one should we use here? Should we use the canonical or the grand canonical? Don't say canonical. We are working with grand canonical ensemble, right? So we should use that one. What is that expression? That is e to the power minus beta E nu minus mu and nu divided by Z. Okay. Let's give this equation a name. Let's call this equation 8. So n bar. And when you go home and derive E bar and P, you will be doing the same thing. Okay, you will write down such a relation. P is a bit complicated. P, you will have to think harder. This one is slightly harder. Okay, because pressure is not fluctuating, volume is not fluctuating. So how do you even get started? If you're not careful with P, you might get an absurd answer. So that one's challenging. Definitely do it thoughtfully. So what do we have so far? We have n bar, which is the same as going to every microstate and doing n nu p nu, is the same as, we can get 1 over z out, n nu e to the power minus beta e nu minus mu n nu. Okay, let's write this down as 1 over z. Let's multiply, divide by beta. We can do that. Summation over all microstates n nu e to the power minus beta e nu multiplied by e to the power plus beta mu n nu. Okay, let's bring one of the beta inside. Let's bring this one inside and multiply with n nu. So this becomes 1 over z beta summation nu beta n nu e to the power minus beta e nu e to the power plus beta mu n nu. If you look carefully, or let's go one step further, actually, just look carefully. This thing, beta n nu multiplied by e to the power plus beta n nu, should remind you of k into e to the power plus kx, where k is beta n nu and x is mu. Okay? K e to the power plus k multiplied by e to the power plus kx. That is the same as t to the power dx of e to the power kx, correct? So these two things together can be written as 1 over zeta b summation nu e to the power minus beta e nu partial of e to the power plus beta mu n nu partial mu. Now notice this does not depend on mu, right? The only thing that depend on mu are over here. So the partial with respect to mu can go outside the summation. This thing can go outside over here because e to the power minus beta e nu, this does not depend on mu. This is just a constant. So this thing becomes 1 over z beta partial by partial mu, partial with respect to mu in every microstate, e to the power minus beta e nu minus beta mu and nu. Have you seen this recently? In today's class, maybe?
Is there an extra beta on?
Oh, yeah,
UN?
totally. Have you seen this today? What is it? It's Z. Yeah. Julia and still remembering names. I'm already there, almost there. You are Anders? No, who is Anders? You are Anders. Yeah, see, because, okay, Anders, next question is going to be for you. So that's the only way I can remember people's names is to ask them questions. Oh, you are Trevor. You have a beard here. What happened to your beard? Well, I can see that. That's a good beard, though. Noah still has the beard. Right. So, okay, so Trevor told me that this is Z of NVT. So what do we have? N bar is equal to 1 over zeta B partial Z NVT by partial mu. That is what we wanted to show, right? So we have just proven this. And again, the same behavior has appeared. The average of a state function is well, I did not quite want to show this, right? Z is dangling up front. So Anders, what can I do with the Z that is in the pre-exponent, which is in the front?
factor those.
Can I bring it inside the derivative? What will it become then?
Derivative of log z.
It was not for you. Would you agree with this? Okay, good. I'm still gonna ask you later.
Why is it z of n vt and not mu?
That was to make sure you're paying attention. Partial ln z mu vt by partial mu. So n bar is, again, the big picture I had wrote over here, that in StatMech, partition functions are generally useless and they are huge, they are big. The reason why everything works is what we are interested in is log of the partition function. Log of the partition function gives us a state function. Log of omega gave us s. Log of q gave us a by kt with a minus sign. Log of z gave us omega g by kt with a minus sign. But that's the actual state function. If you want to get, if you are interested in the average of something which is fluctuating in that ensemble, then you need to take log of the partition function and differentiate it with respect to something. That's what gives you averages. And the second derivative of the log of partition function gives you the fluctuation. So we saw the fluctuation for E in canonical partition function. Next class, I will derive a similar relation for fluctuation of n in grand canonical partition function. And next class, we will see, and you can do it yourself, then next class will be very easy if you do it in advance, that variance of n is equal to 1 over beta partial n bar by partial mu. Wait a minute, this is not the second derivative I was talking about. What did I mess up? Remember, n bar itself is the first derivative, right? So now if you put the value of n bar, which is partial log z by partial mu, so this is 1 over beta partial 1 over beta partial log z by partial mu by partial mu. You see the same second derivative up here. This is what we are going to show next time. And you can already see here that in this equation, on the right side, beta is intensive, right? Temperature does not depend on the system size. Chemical potential is intensive, does not depend on the system size. N bar is extensive for construction. If you double the number of particles, N bar doubles. So this shows us that variance of n is proportional to n, right? Or standard deviation of n is proportional to square root of n. Or once again, standard deviation of n by n is proportional to n to the power minus 1 over 2. Or once again, in thermodynamic limit, the fluctuations in number in a grand canonical ensemble do not matter. So if you are modeling some complicated battery material, you're interested in coming up with some fancy battery, or you're modeling some star in the outside, far from here in some galaxy. If the number of particles in what you're modeling is very, very high, it does not matter what ensemble you take. For practical considerations, it will matter which ensemble you take, but the final result should not depend on that. Okay, so this we will prove next class. This will have even more algebra. Work through it. And what's going to happen after this? I already made a note on the course website, the topics we are going to study. So we have today we did grand canonical ensemble and grand potential. We talked about number fluctuations. We will finish this next time. We will talk about Gibbs entropy, which is a different form of entropy. And it's another way to derive all the ensembles. Gibbs entropy looks like P nu log P nu. It's also related to Shan's entropy in information theory. And I want to give you a flavor for what that is. Once we finish Gibbs entropy, we are going to move. If you look at the syllabus of this course, the way we had it structured was, the part 1 was foundation of statistical mechanics. And we are basically coming to the close of part 1, which is fluctuation and things like that. In the next part, we are going to do more applications. And we will start with the simplest applications. You already saw one application, which was the two-state system and particles, right? So we will do things like that. Some applications you have in the homework, we will be doing more of those. These will be non-interacting ideal system. And you would think, who cares about non-interacting ideal system? Everything involved is interacting with each other. But still, it's quite useful. And we will cover a lot of material just in the limit of non-interacting ideal system. That will take us a bunch of time. Then we will move to interacting systems, which is classical fluids, things like liquids and things like that. We will talk about things known as radial distribution functions, G of R, and things like that. The math will be a different type of nasty, but there will be still a lot of algebra. And then in the fourth part, we will do phase transitions and critical phenomena just a little bit. And in the fifth part, depending on time we have left, we will look at some special topics. I also wanted to mention the first midterm is, like I said, take home. The second midterm will be a research paper. So you will be split in groups of 3, definitely assigned by me. So it won't be all the biophysics folks hanging out each other. No, it won't be like that. It will be very, very mixed. And I will have a choice of 5 or 6 papers. As a team, you will discuss which paper you will pick one paper, and you will make a presentation on that paper. You will go through it, everything. Okay. So you will have to form consensus on which paper to study and things like that. That will be the second midterm. The final will be take home. That's for sure. Sorry, the final will be in class. That's for sure. Any questions about anything?
Can you say that the first midterm is only going to take us around written a 2 to 3 hour exam? How long do you think the homework should take so that I can like scale the time appropriately?
I refuse to answer that question on religious grounds. Look, I have done a PhD myself. I should stop recording. Bye, Noah.